Draw the moment diagrams for the frame. Assume the frame is pinned at C and members are fixed connected at B. To solve this problem, we'll need to divide this frame into two sections, AB and BC. And before we start drawing its diagrams, we need our reaction forces for this beam. So we can start with BC by drawing its free body diagram. So at BC, we can have BX and BY and its moment. And on the other side for C, we have horizontal and vertical. Reaction forces. And then we're going to convert our uniform distributed load into point load. And this comes up to be 1,800 pounds. Now we can start using our equilibrium equation. So let's sum the forces in x direction. We're going to have positive bx and negative cx, both equal to 0. And this will be our equation 1. Then vertical forces, you can have positive by, positive cy, and negative 1,800 pounds. All of this is equal to 0, and this will be our equation number 2. And then we're going to take moment above the point C. We're going to have 1,800 counterclockwise, and it's 3 feet away. Then we have clockwise by, 6 feet away, and we have our moment counterclockwise at B, all equals to 0. This will be our equation number 3. Now we can proceed to our second section, which is AB. For this, we're going to start using our equilibrium equations once again. So we're going to sum the forces in x direction. I'm going to have cos 45 degrees times FA, and then negative BX, all equals to 0. Simplifying it further, we can have our solution as root 2 over 2 times FA. This will be our equation number 4. Then we're going to sum the forces in y direction. We're going to have sine 45 degrees times FA, and then negative BY equals to 0. Solving for Vy, we get our solution as root 2 over 2 times FA, and this will be our equation 5. And here we can also observe that both Bx and By are similar, or same. Now, finally, we can sum the forces about the point B. So we can have moment B counterclockwise, and then clockwise FA times 8 equals to 0. Simplifying moment B, or moment B, and we're going to get 8 times FA, and this will be our equation number 6. Now we can plug the value of equation 5 and 6 into equation 3. So we're going to have 1,800 times 3, which is 5,400. Then negative root 2 over 2 times FA times 6. Take away 8 times FA equals to 0. And for FA, we get our solution as 441.081 pounds. Now we can plug the values of FA into rest of the equations and get our value for each reaction. So our By and Bx are going to be 311.892 pounds, and then our moment B is going to be 3,528.650 pound. Then our Cx is going to be 311.892 pounds, and then we finally have Cy, which is going to be By, which is 311.892, take away 1800 pounds. It's going to be positive 1488.1.8 pounds. Now that we have all the reaction forces we needed, we can proceed with our shear and moment diagram. So first we're going to draw our shear and moment for BC. So for both BC shear, we're going to begin at positive 311 point, and then we have a uniform distributed load of 300 pounds, which we found to be 1800 pounds. So therefore 311.89 take away 1800, we're going to get our value to be negative 1488.108, and this curve is going to be first ordered, therefore in a triangular shape or straight line. And then we have our reaction from Cy, which is positive 1488.108, which will bring us to 0, and that's our solution. And now one thing before we proceed to moment, we need to find our intersect for this curve, because this will be where our moment will be the highest. Okay, to do that there are a number of ways, and the easiest in this situation is to simply have the load equation and then integrate it. So you're going to have 300 pound, that's our load equation, and then integrating this, you're going to have 3x plus our constant, and we know when x is 0, our shear is 311.892. Okay, so that's that, and now we can find where our shear is 0 by simply solving for the x, and our value for x comes up to be 1.03, pardon me, 1.040. Okay, now we could proceed to our moment diagram. From our shear diagram, we know that this point will be where our moment is the highest, and to find this value we just have to take the area of the positive area or the shaded area in the shear diagram. So it's going to be simply 0.5 times 311.892 times 1.040, and this comes up to be 162.18384. But before we do that, we also need to remember that we had a moment from joint B, and that moment was 3528.65. So this means that our moment is going to begin at 3528.65, and then we add this new value of 162 to get our highest point, which is going to be 3690.834. And because our shear diagram is positive and it's decreasing, we're going to have concaving downward curve, and it's going to be our second order curve. And similarly, now we're going to get our ending moment by finding the area under the negative curve for the shear. So it's going to be negative 0.5 times negative 1488.108 times the distance left. So it's going to be 6 take away 1.040. And this comes up exactly to be 3690. Therefore, we'll be reaching R0 and confirms that our equations are correct. And the curve will be concaving downwards because this is negative increasing. And it'll be second order. Now we can proceed to our next section, which is at 45-degree angle, or shear begins at 45-degree angle, and it's going to be FA. FA was positive 441.081, and then it's going to continue in a straight line all the way for 8 feet, where it's going to be our BY, or in fact, it's going to be a little bit tricky. Reason being, our BY is in a plane that's normal without the 45-degree turn. But now, in this new case, our BY, we need to convert into our tilted angle in order to get the right value. So it's going to be simply sine 45 which is our denominator, and our numerator is the value of BY, which was 311.892, and this will give us our tilted vector value. And this comes up to be 44.079. It's a little bit different than our value of the shear, and that's because of the number of significant digits I've used in my calculator. But if you use all the significant digits, you should be able to get exactly the value as our value of FA. But anyways, doing that, it comes down to 0, and this confirms that our equation was correct. Now we're going to use this data to find our moment diagram, which is simply going to, in the beginning, it's going to be 0 because there isn't any moment at point A. And then we're going to proceed to have our moment, which is the area of the shear, which is 441.081 times the distance, which I believe is 8. Yes. And solving for that, we get our solution as positive 3528.6465. And that's going to be a straight line or straight slope, which is our first order slope. And then at this point, we have our moment at B. That will bring us back to the 0 point mark, and solves our solution.